Hi, my name is Sosa, and I'm here to explain the special theory of relativity by Einstein. Einstein declared that there is no such thing as an existing trajectory, but only a trajectory relative to a particular body of reference. Now let's consider this. An object or an event is considered in motion because it is moving away from an object at rest. Let's imagine a train is moving from the perspective of someone standing on the platform. But if someone is standing inside the train, the space outside of the train is in motion. Einstein takes into consideration the law of inertia. This fundamental law of mechanics, the law of inertia, says that a body removed sufficiently far from other bodies continues in a state of rest or of uniform motion in a straight line. When we use the word straight line, we are going back to elementary geometry. This geometry is based on axioms, otherwise known as Euclidean geometry. From these basic concepts came the Cartesian coordinate system. The laws of Galileo and Newton can be regarded as valid only for the Galilean system of coordinates. This is an example of Cartesian coordinate system. They are very simple coordinate systems that don't take into account the curvature of the Earth. Let's picture a bird flying over the subway in a different direction. The train is given the coordinate system k relative to the embankment. The raven shall be given the coordinate system k1 relative to the train. The special theory of relativity states that if a relative to k1 is a uniformly moving coordinate system devoid of rotation, in other words, if the bird is moving in a straight line, then natural phenomena run their course with respect to k1 according to exactly the same general laws as with respect to k. From this conclusion derived the theorem of addition of velocities, employed in classical mechanics. Classical mechanics describes how bodies change their position in space with time. Because the word space is ambiguous, Einstein replaced it with a motion relative to a practically rigid body of reference. Let's suppose that a woman is walking inside the train towards the same direction of the train. She's walking with a velocity of w, and the train is moving with a velocity of v. What is w relative to the end? The logical thing to do here is to add the velocities of the train to get the velocity of the woman. An equation looking like this: w equals v plus w. This theorem, however, cannot be maintained due to the properties of the propagation of light. The propagation of light has a velocity of 300,000 kilometers per second. There is constancy in the velocity of light. It does not depend on the speed of any body. This being said, the equation of the theorem of addition of velocities is not valid. It cannot be. If we were to make the woman walk in the opposite direction, and if we replace the woman with a ray of light, the equation would change to w equals c minus v. W here is the velocity of the ray of light. C would be the constant velocity of light, 300,000 kilometers per second, and v is the velocity of the railway. The transmission of light must, according to the principle of relativity, be the same for all system of coordinates. So we can either abandon the law of propagation of light, which is necessary for electrodynamics, optical, and electrodynamical phenomena, or the principle of relativity. Here we must abandon the principle of relativity, and Einstein derives the special theory of relativity. Can there be a relation between place and time of the individual event relative to both reference bodies such that every ray of light possesses the velocity of transmission c relative to the embankment and relative to the train? The answer is yes, there can, with a system of equations known as the Lorentz transformation. Let's give the event k relative to the embankment the following coordinates: x, y, z, and t for time. For the event k1 relative to the train, let's give the coordinates x1, y1, z1, t1. With the following system of equations, We can give both events the same place and time. Einstein noticed, however, that objects are not necessarily the same length when measured in motion as they are when they are at rest. Let's imagine we place a 1-meter rod on the x1 axis. What is the length of the rod relative to the system K? To find the answer to this question, we find the end and the beginning of a rod at a particular time, t, of system K. The distance between the rods is the root of I times v squared over c squared of a meter. Here we see that the rod is shorter when in motion than when it is at rest, because the rod is moving with a velocity of v relative to k. There is a contraction in the rod. Einstein also noticed that there was a difference in time between two events. Let's imagine that a clock counting time in seconds is situated permanently at its origin. Another one is situated at the origin of K1. Time elapsed between two strokes of the clock is not 1 second, but I over the root of I minus v squared over c squared. Because there is less distance traveled in between, as we saw with the rod, the clock goes slower. Here we see that the general laws of nature are covariant with respect to the Lorentz transformation, and the theory of relativity becomes a heuristic aid. The Lorentz transformation allows for the variable c, the velocity of transmission of light, to be the same in both k1 and k, and for any ray of light advancing in any direction for that matter. Let's say a light stimulus advances in accordance with equation x equals ct. According to Lorentz transformation, the relation between x and t involves a relation between x1 and t1. We substitute x for ct in first and fourth equation of the Lorentz transformation, from which, by division, the expression x1 equals ct1 immediately follows. The velocity of transmission relative to k1 is also equal to c. The special theory of relativity can be tested with electronic ions. In physics, the law of conservation of energy and the law of conservation of mass used to be independent from each other before the theory of relativity. Einstein came to the conclusion that a body with a constant velocity of v, which absorbs an amount of energy in the form of radiation, has energy increased by an amount equal to E0 over the root of I minus v squared over c squared. The required energy of the body comes out to be m plus E0 over c squared times c squared over the root of x minus v squared over c squared. Therefore, the body has the same energy as a body of mass with a velocity of v. The law of conservation of energy becomes identical with the law of the conservation of mass, considering the system neither takes up nor sends out energy. From here is where Einstein derives the equation E equals mc squared, but that is later explained in the general theory of relativity, which is much more complex than the special theory of relativity. Thank you for listening. This has been the Special Theory of Relativity by Einstein with Anna Sosa.